All right. Hello, AP Calculus BC students. We're here at Avon Community, the Avon Community, I guess, not Avon High School necessarily, because nobody's allowed there. But this is e-learning day number 7 and Thursday, March 19th. And I'm working with my BC students today. Basically, well, how would you describe it? We're kind of cleaning up some loose ends over Euler's method. Which is something that I actually taught my students last year. They're in a 2-year program. And then we have 7.9 on the new CED, which is Logistic Growth, which we had a lesson for on our last e-learning day. So those are the first couple of things that we're going to take. Just if we have any quick questions and answers over that particular homework assignment. That homework assignment is something that I decided I will not necessarily put together a Schoology submission for you. You'll still have the quiz that covers both of those topics, 7.5 and 7.9, and that will be open to you. I believe I'm going to open that after the Zoom session tomorrow, you guys. And then you have until midnight to complete that 5-question quiz that covers these 2 topics. And then that will pretty much take care of us through spring break. And then we have this activity that I'm going to share with you today. I'm going to actually get it posted tonight. And I think part of our Zoom session tomorrow will be discussing this one. It's a fantastic activity that my friend Brian Prasswater from Speedway High School here in Indiana wrote like in the middle of the night 2 nights ago. And it's very cool. It's 26 questions that covers almost every important concept from AB. So that's very, very neat. So. All right, so let's go ahead and I tell you what, let's open up the wonderful Euler's method. Wow. Um, Let me guess, we're not a big fan of this assignment, am I right? And I could certainly see why, because of the fact that you're doing many steps for these problems, right? You're using as many as 4 steps, which is certainly probably 2 more than what you would be asked to do on the AP exam. And it doesn't help the fact that some of the problems get so bogged down with some ugly decimals. And I'm going to try to amend this. There should be a calculator icon, throughout this entire assignment. But the calculator icon, you want to kind of be careful because you don't really want to use your calculator's capabilities in terms of like programming an Euler's method procedure. Because if you think about it, those of you who code really well, could you like write a program that does Euler's method? I mean, I'm thinking it might be like 4 lines of code, maybe. You're just talking about taking two values, an x and a y, plug it into a derivative formula that you would define, and then manipulating that to a tangent line, and then changing the x value accordingly, right? So it shouldn't be very tough. But they don't want you doing that. We probably also don't want you programming things into your spreadsheet capabilities of your calculator, because Euler's method is likely going to be a no calculator problem, but it would be a pretty chill problem in terms of the decimals that you would encounter. So I'm looking through and checking to see, can we do either 2 or 5 on the Euler's method homework? I tell you what, let's do that. All right, if nothing else, we can get these problems here started, and then I can share my solutions. I don't know if you guys have checked Schoology, the discussion board. It actually had a little activity. I posted a pair of, or some solutions to a few of the problems, and I was soliciting whether or not I had made mistakes, because I kind of did them really quickly. And I thought, you know what, that would be a good discussion for you guys to look through those and see if you found mistakes. Probably found a couple, I think, already, and we've work them out, but I have not changed the key, so whatever mistakes are there still are there, so that you can still kind of look at them and find them. So for number 2, it says use Euler's method to approximate the value of f of 1 if you have your differential equation equivalent to 4 quantity x plus y squared, and f of 0 is -1, and we are using 4 steps, it says. So it is a complete choice up to you if you'd like to set up your table the way that I do, right? You have an ordered pair, x followed by a y, and then you've got a derivative value that you will have to use. And then after that, it's pretty much your tangent lines equation. I mean, that's going to make up the rest of this chart. We don't have to worry about finding the dy value or the capital Y like a pair of the tables asked us to do. I think one of Mackenzie's questions revolves around that kind of a problem. So we can discuss that when we get to number 5. But at the beginning of this problem, it gives you the fact that f of 0 is -1 initially. So those turn out to be your first x and y. And then you perform your derivative, which is just basically 4 times the quantity of the 0 plus the -1 squared, which would give us 4 times 1, or 4. And at that point, we can go ahead and write the equation of our tangent line. I might want to move this guy over because that derivative could get pretty rough after I get some decimal values. So if we use the good old point slope formula, y minus -1 would equal our slope for quantity x minus 0. And while I'm doing this, I'm going to call up what I have of my key just to make sure that I don't make any other mistakes with this. Okay, so that looks fairly acceptable. And if we go ahead and solve this for y, which is going to be to your best interest here in a moment anyway, we would have y equal 4x minus 1. Okay, so come AP exam time, honestly, you're halfway done. You get to this step, you probably only have to do one more iteration. So this problem here, it did not tell you what the step size was, right? So you have to figure that out on your own. See, if you're going to jump from a 0, that's where you're starting, and ultimately you want to get down here to be a 1 with 4 equal steps. And you know what? I'm telling you, the word equal should have been mentioned there, because otherwise you can pretty much willy-nilly use whatever steps you want. So let's put that word equal in there. And then you guys realize that each step is going to be a 0.25 or a 1/4. Now, notice what I do here. I write the fraction version because I think that fractions are going to keep you from having to use your calculator a little bit longer. That's going to change. I know that by the time you get to the last line, it's going to be pretty bad. But I think that's pretty much the case here. Let's go ahead and just complete this line here, and then I might pull over my key. So if we have 1/4 as our new x, you always go back to this y equation to get your new y. So 4 times 1/4 is what? 1. 1 minus 1 is 0. So there's our new ordered pair. And so now our differential equation is going to say that 4 is equal to quantity 1/4 plus 0 squared, which would be 4 times 1/4, which is 1. And so our tangent line is pretty easy to write. Perfect example of AP level difficulty right here, no question. The question might say evaluate f of 0.5, right? Approximate f of 0.5. Maybe I should have done that, right? So this is just y equal x minus 1/4. And then we keep going with increments of 0.25. And then to find the new y value, you would plug half in for x. Half minus 1/4 is 1/4. And then you just keep it alive, right? Now, if you'll allow me, I'm going to drag this in. And I think this is one of the questions where there was a mistake. Gosh, I can't remember who had pointed this out. Pravir had pointed some mistakes out. I want to say that somebody else had done a really good job. I apologize if you're here and I'm not acknowledging you. Hey, I just lost that document. Where is it? There it is. Let's make this a little bit bigger, shall we? So this is just my Word doc. And I want to say that this is the correct overall solution, wouldn't you say? Now, you can see how I was very proud about continuing this with fractions, but I'm not going to even for a minute pretend that I avoided using the calculator. I think by the time I got to this guy here, this 13/16, and I had to square him and then figure out what the slope was going to be, that's when the calculator really came into play. So looking through the chat to see if there's any other questions about this. I'll tell you what, if you guys get these answers, these really hideous looking answers, number 2, it's 569 over 256, or as a decimal 2.223. I mean, you got to feel pretty good about yourselves. But let's look at all the horrible, hideous arithmetic that had to go on. And for those of you outside of Avon watching this, I know for a fact that this is not what you're going to have to do on the AP exam for the BC test. Like I said, they might just have you figure out what is f of 1/2, and then you could say, oh, it's approximately 1/4, and then you're done. And you demonstrated that you know Newton's method, or I'm sorry, Euler's method. All right. If we want to look at problem 5, I'm going to have to take another look here at the Smart document version of 5. That was the one that we're looking at, right? So it says, consider this differential equation. Y of 0 is 0. Use Euler's method with 5 steps. Are you kidding me? 5 steps. How did this work out? I mean, was the computation just bogging you down, or was it part B maybe?
I meant 4. 5 is okay, but I meant 4.
Oh, you meant 4. Okay.
Sorry.
Not a problem. Not a problem. 4 is one of the ones with the chart. Okay. Yeah. This one is certainly going to require a calculator. You know, and it implies that using a calculator is acceptable as long as you don't program some sophisticated Euler method thing. So this chart, to me, is still kind of not a means by which you can really officially find these answers, in my opinion. I mean, I still have to kind of make my own larger table so that I've got some room to work. And can do the first few rows here and see what happens. First x is 0, 0. Boy, that's pretty innocent enough, right? And then the derivative, well, that's the sine of just the 0, which we know is 0. So the equation of the tangent line would be, well, y minus the y value equals the slope of 0, quantity x minus the x value. And that segues into y equals 0. So if we want to pause here and we could fill out our table, we know that the y is 0, the dy dx is 0, and then remember the dy, in this case, the dy is nothing more than dy over dx, right, times the dx, and the dx is the same as what in this problem? Well, it's not labeled as h, right, but it's the step size. So we have to figure out that the step size here looks like it's 0.25, right? But those are going to cancel and give us the dy. So if you just take your dy dx column value and multiply it by 0.25, it's going to give you the dy, okay? And remember, you can't figure out y until you've done part B, right? Part B is the actual solution to this differential equation. And what we're basically wanting you to do is just kind of like look at the progression of this along with the dy column. And you know, if you were really super motivated, you could like plug in these values into the sine function to see how close our approximations might be, but it's not something that you have to do. So we go to the next column and we have 0.25, or the next row that is, and we have 0 for our y value. The sine of 0.25, this is where it all comes to a halt, right? The sine of 0.25 is something that it's not very workable in our opinion, so we just have to pull out the calculator. And you guys could do clever things if you wanted to. I mean, you know, you could start to make a table of sine values, or you could just simply pop this in. Make sure that you're in radians, right? And then 0.2474. I don't even know if all that's going to fit.
How about we build a Taylor series for sine?
I know. It'd be easier, wouldn't it? 0.247. And then here's your equation. Y minus the y equal the slope x minus the x0, and you're off and running. I think that would be your equation, which
Isn't x
this,
0.25 instead of x
oh
minus 0?
yeah, it's my, yeah, that's going to change things. I got so used to wanting to have that x to be 0, which that is going to actually cause us to have something that we have to work on. So 0.247 times 0.25, it's probably pretty close to 1/16, but it's not going to be exactly. So 0.247, I feel bad. I should have probably used that more accurate number up there, but 0.061, we'll call it 0.062. And you can tell I'm just compromising all of our rounding because I just don't think that we have enough room in these boxes. 0.062, I think I said it was. Sure. And I think we could then fill out this next row where the y value we know was 0, the dx or the dy dx was 0.247. And then the dy would be those two multiplied together. And then are we starting to perhaps see what the role of the dy really is, maybe, especially early on, how it's kind of like the y-intercept of those first two equations. So I don't know, Mackenzie, what do you think? Do you want me to keep a rolling with this? It's tedious, you guys, and I'm going to tell you what, for those of you here, if you choose to do either 3 or 4, I'm pretty happy because they're essentially the same problem. And I think it's a neat experience, especially when you get down to the graph. But to do both of those, I don't really know what more that you can gain, especially since you guys have been through series, right? And you kind of understand the nuances of how we can do a lot better using a series because we're not just confined to using a straight line and moving that line ever so slightly to try to approximate. You see what I'm saying? With our Taylor series, we can actually manipulate by using curves, and bending curves around other curves is a lot more powerful than trying to take a line and reorient it. So hopefully that kind of makes sense. It seems like this is very anticlimactic now that we've already seen Taylor series. So let's take a look at, we did have a
Mr.
request.
Record,
Yeah, go ahead, go ahead.
on number 4, the y value, what exactly is that? I know you've said it.
The
But I
capital
was
Y,
confused.
the capital
Yeah,
Y value.
that y.
That would be what would happen if, I'll tell you what, I'll do this really quickly for you guys. Let's say we go through B here and we separate and integrate, which is something that we as BC students need to review since we haven't solved too many differential equations in a while, but you guys are going to pick up on that really fast. It's one of the first AB major topics that I was going to review with you guys. So we'd have y on the left side and, ooh, negative cosine of x, is that right? On the right side, plus a constant, okay? Now remember, we can find that constant by using the initial condition, which in this case is 0, 0. And that would give us 0 equivalent to negative 1 plus c. So that forces our c to be positive 1. So therefore, this equation, y, is negative cosine of x minus or plus 1, right? Now, this capital Y here is the actual value. So this can get kind of confusing because you have a lowercase y here in this tangent line and a capital Y here. So that's why on my key, I called this capital Y before I wrote my final answer so that you kind of knew which is which. And so if we just plug 0 in for this, we have negative 1 plus 1, so that would be 0. If we were to plug, well, 0.25 is going to be a little tougher, but I want to show you this nonetheless. So if I take negative cosine, let's do this the right way, negative cosine of 0.25, and then I add 1, I'm looking at 0.031, let's call it. Now, let me see if I can show you what's really going on here. And this is going to be much better for you to watch than doing both problem 4 and 5. Remember how we can actually graph slope fields? If we go into a graph screen and we tell the graphing calculator, hey, let's graph some cool stuff here, and let's now graph differential equation. Well, remember that differential equation, it was dy dx equals sine of x. Well, notice that that's what we have up here, right? Y prime, right? That's the dy dx, and that's equal to sine of x. And I know that I've shown you this before in the past, but it's been a long time since you guys have worked with this. And then moreover, we have an initial condition, don't we? 0, 0. So if I throw that in there, what I have is the slope field that is generated. And through that slope field, we know that we can have a whole variety of different curves, right? This just being one of them. But this curve could have been shifted vertically upwards or downwards, depending on possibly what that initial condition was. But do you agree that this curve looks like it could be negative cosine of x plus 1? Right? Now, the negative cosine of x is kind of tricky because for negative cosine of x, you have to think of the cosine curve, okay, and it gets like mirror imaged around the x-axis, okay, so it's kind of starting down here at -1 and then coming up and then doing something like this, but then the add 1 just shifts it all up vertically 1 unit, okay? So essentially what's going on here is if we can do a side-by-side, okay, side-by-side, didn't work real well, did it? Let's try a side-by-side here. Let me just minimize this a little bit. My computer sometimes doesn't like to do side-by-sides with Zoom. See what I mean? So what's going on here? I better not manipulate this too much more. But what's happening is at 0.25, which it's going to be a little tough to see because I probably ought to zoom in a little bit. Maybe I can. Maybe let's just do that. Let's take this out to like 1 for a moment. Yeah, well, that's nice, isn't it? Sorry, you guys. I need to do the same thing with this size so it's not crazy. And oh, you know what I better do as well? I'm not real happy with the resolution here, so I'm going to tell the calculator on this graph, let's give me some more resolution. In other words, let's calculate more points that are closer together, not just every 10th of the way, but how about every, hey, let's go crazy, every 1,000th. All right, this shouldn't take the calculator too long to compute. No, it didn't. So there we go. We've got a little bit better view there. And then one more thing I'm going to do, guys. Let's change this upper boundary so it doesn't go so high, maybe +1, and we'll do the same thing down here. Okay, now I think we can kind of look at this a little bit better and say, okay, at 0.25, which would be right about here, right? We seem to have an exact value of our curve, our solution curve that's, what did it say? It said it was point, can you guys read that? 0.071, is that, or 0.031? See, my eyes are so bad. Let's just make this a little bit bigger. 0.0, I think that was a 3.1, maybe, right? I have it on my calculator if I want to check. What did it say? Oh, nope, you know what? Because I cleared my document. But anyhow, it is definitely a very small number. That 0.031 is correct. That's kind of what we're doing. We're just figuring out what the value is on that curve. But at the same time, we have to understand that that value is not necessarily going to be the same one that we got if we use the tangent line. So if we continue to figure out what this next y value was by plugging 0.5 into this mess, it's probably going to be close to that 0.031 number, but it's not going to be exactly. So that's kind of what's happening, right? It's just showing you a lot of visual of what's going on with all the math in the table and so forth. So, okay. Noah asked, would you have to find dy and capital Y on the AP exam? And that is, I've never seen it. I've never seen a student that a situation where you'd have to do that. And I'll be honest, I don't see too many textbooks that have you do this. This is just something that I picked up from a few sites. Master Math Mentor kind of used this in his materials, and I kind of liked it because it gave a little bit more flavor to Euler's method. It just didn't become sort of a broken down, just follow this step, do this step, and then that step, and then bam, you have an answer that's probably going to be an easy point or two on the AP exam. It gave it a little bit more meaning. So, all right. I had a request to go ahead and look at 5 Part B. So, and I don't mind doing that. It says the equation y equals c e to the negative t plus t is a solution to this differential equation above. It says to take the derivative of that y and then show that it is the same as the differential equation above. So yeah, like we can certainly do this. And what's really nice about problem 5 is that I can't really tell you how to solve that differential equation to come up with this answer. This is something that I'm going to embarrassingly say I think I may have forgotten, because this is a little bit more in depth or higher difficulty level, because it's not a separable differential equation. It's really difficult to get y and t by itself in this problem. So we have the solution. All that they want us to do is to take its derivative with respect to t. So if we do that, the c is a constant, and then we take the derivative of e to the negative t, which of course is e to the negative t, but then whoop, don't forget to multiply by the derivative of negative t, which is -1, and then of course you have your +1 here, right? Now, let's see, what do we got? This is going to become negative c e to the negative t plus 1. Now, this is the part that most of you were probably, comfortable, right? Maybe you guys were able to get this far, but we're like, well, how does that, compare to the original? It's like, how on earth is this thing that was supposed to be highlighting? How about this thing here looking like this thing here? I mean, I just don't see it. But I think if you do a little bit of manipulation, you just might see it, right? And that manipulation, I think, comes in the form of going back up to the original. Now, let's make sure that this isn't a circular argument here, though. So if we were to, let's say, subtract CE to the negative t over to the left, and then subtract y over to the right, would we be allowed to replace this negative CE to the negative t with negative y plus t? I don't see why we couldn't. And once we do that, do you guys agree that they match at that point, just in a different order? So I think that's kind of what 5b is asking you to do. It's like finding a solution, or I shouldn't say finding, but you're verifying a solution to a differential equation, which we did that a little bit last year. And it is a topic in the CED. I devoted a whole day's lesson to that with my juniors this year. So, all right. Shall we turn our attention to the more interesting assignment now, the logistic growth? Again, I would certainly encourage you guys to check the solutions that I've posted in the discussion board, and selfishly, I am using you guys to try to fish out all my wrong answers, but I think that would be good for you. And if you haven't already, definitely look at problem 6. I like problem 6. It's very AP style, and fortunately, problem 6 is by far the shortest of these problems. So I can see how this could certainly be a problem that you could end up solving on a test like the AP exam. Section 9. All right. The first request I thought was 5 on this one. It kind of goes back, or 6 on this one. All right. That's the one I figured you guys would be talking about anyway, number 6. All right. It says, which of the following differential equations could model the logistic growth in this graph? Which of the following could model the logistic growth in this graph? what you're looking at here. I don't want you to look at this as the traditional logistic growth. I had a really good conversation with a colleague of mine, Brian, just last night about this particular problem. And it is classified as a logistic growth curve, but it's not our sort of AP style logistic growth curve. And the reason it's not is because its lower boundary, its lower starting point begins somewhere pretty far away from zero. And that's not really analogous with the logistic growth that we are going to be talking about, because we're going to talk about, like in the case of the coronavirus, patient 0 would probably be one person. So that graph would start right here, if I can get my pen activated, probably with a y-intercept of 1 to indicate one person has this disease, and then what happens from there, right? Now, with population growth, without turning this into a biology lesson, let's say you need at least 2, right, to start that. But with this situation, it's completely different. So I don't want you to be too worried about this, because it's likely that this is not going to be seen on the AP exam. But I like this. I like this from a college level Calc 2 perspective. So let me see if you guys could eliminate which one answer has no chance of being correct. You want to put that privately in the chat for me? Which answer, A, B, C, or D,
C.
would you quickly eliminate? Okay, good. Some of you are eliminating 2, and that's fantastic. That's fantastic. Majority of you are saying get rid of B, and I agree 100%. B you're going to get rid of because it doesn't have that logistic look to it. This is normal exponential growth, right? If we were to solve this and graph it, and not that we have to, but if we were, this is kecked, which is just going to look like this, right? This is unfortunately what coronavirus looks like right now in America and in Italy, all right? But we know that it's not an unbounded an unbounded exponential growth. It will be bounded, okay? Now, a lot of you also said that you're going to eliminate D, and I love that. I love that. D is eliminated because what is the carrying capacity of the equation in D? Or what is the L value in D? Well, good. Got a private message that had it, yeah. Well, if you have trouble with that, remember that this doesn't quite look like the general form of a logistic differential equation until you have a 1 in this spot, right? So if we were to factor out a 1,000, 35 times 1,000 would be 35,000. Wow, that's a pretty massive K value. And then we would have 1 minus, and then what do you get when you factor 1,000 out of an M? Well, that would be M over 1,000, right? And remember, 1 minus the population over L is what resides in those parentheses, right? With K times the population out in front. So there's your L, that 1,000, okay? By looking at the graph, it's pretty clear that the carrying capacity, or L, if I can call it that, would be 50. So that's another way that you can get rid of D. Now that brings us to 2 very unusual options that I still want to leave a little bit of mystery to this. And if we have to, we can make sure that we discuss this tomorrow. But when you get down to this, you cannot rely on the general form of the differential equation result for a logistic curve. In other words, you can't use the L over 1 plus Becht for this because these aren't of that form. But I will give you a hint. Understand that each one of these represents the slope of the tangent line, right? And you can probably figure out around in here what the slope of the tangent line might approximate, what it might be for a various value of m. You can't throw a t in there, but you can throw an m in there. And I think one of those will make sense and one of them won't make sense. And hopefully that'll give you guys enough insight to continue with that. Okay. I'm going to check something in Schoology here real quickly. I want to say, did I make a submission after all for this? What is going on? You know what, guys? I do have a submission for this, and I'm going to go ahead and have you do it, but I'm just going to tell you, you will get a 10 out of 10 if you get more than half of these right. Okay. And if you don't get more than half of them right, I'll probably just reopen it up for those people to redo it. Okay. So I kind of wanted to put a little bit something on you guys to input for the end of the week, just so that we've got, you know, some grades that we had in the grade book and whatnot. But go ahead and make sure that you do that. I don't have any kind of input for the Euler's method homework. But for this one here, after you work through these 6 problems, go ahead and enter them into Schoology. It's a one-time submission. It's reviewable. I also think it's resumable, but I don't think you need to resume it for so short of an assignment. And it's open now. All right, it is open. And I think the due date, I think it's due by 2 o'clock tomorrow. All right. So if you wouldn't mind doing that, that's going to give me some data to use in our session tomorrow. So if a lot of people are struggling with a certain problem, I'll definitely show the full solution at that point. Okay. So is that, you guys okay with that? That's a pretty minor thing, isn't it? Pretty minor thing. Okay. Is there anything else with logistic growth here that's concerning you? Seems like the other 5 problems were certainly a little bit more traditional. I'll be monitoring my email tonight, so that if you guys have a question, I can certainly bring it up. So yeah, Continental Math League, what's going to happen there is the fact that obviously we're not going to be back in a normal traditional school setting until May 1st. And the fact that we have carte blanche with the CMLs now, in other words, we can take them late, and that's wonderful. I'm thinking that, let's put this scenario out there. We actually get to come back to school the first week of May. Things start to kind of become normal. We figure out the AP exam maybe is going to be administered in the middle of May, right? We're going to focus on that. I'm not going to do CML stuff, you guys, before the AP exam, not at this stage. So we take the AP exam in whatever form it's administered, and then there's probably a few days that we have left, right, before you guys graduate. I figured on those days we can do the CML. Even if we have to do the 2 on back-to-back days, or maybe 1 day or 2 days apart, I don't see a problem with that. And that's how we'll handle it, because, you know, we're only 4 schools are tied for first at this point, which is pretty rare. You know, normally there's still a logjam of schools, and I want to kind of stay there. I know you guys want to stay there. So I don't want to bail out on it yet, but we'll focus more AP and then worry about the CML later. That's a good question. That was a very good question. Do you guys want to see this surprise? This very cool surprise here. Let me show this to you. Let's show you a journey through calculus. Actually, I better not show you the key for it. Let me just show you the actual document here. This will blow you guys away. This is awesome. If I can find it. Not having much luck. Here it is. But what I'm going to do is post this probably before tomorrow's session. And I want to have you guys work on this a little bit through break, and certainly after break would be the time that we'd want to have this due. And I might even have you maybe throttle back on the CMLs at that point. All right. In fact, I would probably rather you focus more on this document than the CMLs. And basically, as you can see here, you're given a graph of f prime, a piecewise function of h, and a table of values for g double prime. And from those three problems, from those three representations, you can answer 26 different questions from AB calculus, like finding the value of k where h of x is continuous, going on to determining whether f has a local min, max, or either. And on each page, we replicate those three representations, so you don't have to flip your pages back and forth. And it just keeps going and going and going, you guys. And it's calculus, A to Z, right, for your AB review. So I think that this would be a really good document for you guys to look at, you know, in conjunction with your mock exam that you have. And I think that would be a nice thing to kind of brush up on. So that's what we have on tap tomorrow. So tell you what, I'm going to go ahead and stop the recording and thank everyone for joining us asynchronously. Teachers across the country, if you happen to be watching this, best of luck with you. You can always reach out to me if you have other questions about hardware, software that we're using for e-learning here at Avon High School, or other resources that you want to use with your students. But my students here in the chat, hang on and we'll close down here together. But everyone else, enjoy the rest of your day.